In our last video, we made the claim that according to the rules of quantum physics, it's possible to arrange an experiment in such a way that our little game of quantum shells yields seemingly contradictory results. Namely, that whenever I open all of the shells in the top row, I will count an odd number of p's, but whenever I open one top shell and two bottom shells, I'll always count an even number of p's. In this video, we'll actually walk through the quantum experiment that leads to that result. To follow along, you'll probably want to have at least a basic understanding of the postulates of quantum physics. But even if you don't, I think you'll still find the next video in this series interesting, where we talk about what it all means. So, let's get back to our experiment. Each pair of shells represents a quantum measurement of the spin of a particle. If we uncover the top shell, we measure the x component of the spin, represented by a certain Pauli matrix. If we uncover the bottom shell, we measure the y component, represented by a different matrix. Each spin measurement has to give either +1 or -1, since these are the two eigenvalues of the matrices. A measurement of -1 corresponds to there being a p. A measurement of 1 corresponds to there being none. One way to determine if there's an even or odd number of p's under any set of shells is to take the corresponding spin measurements and multiply them together. Since we're just multiplying 1's and -1's, the product will also be +1 or -1. If there's an even number of p's or an even number of -1's, the product will be 1. If there's an odd number, the product will be -1. To describe states, we'll use the common shorthand notation of an up arrow representing the vector 1, 0 and a down arrow representing 0, 1. Using this notation, you can see that an SX matrix turns a up to a down and a down to an up. An SY matrix turns it up to a down with an extra factor of I and turns a down to an up with a factor of -I. We set up the experiment by preparing 3 entangled particles in the state up, up, up minus down, down, down over the square root of 2. We then send one particle to each pair of shells. What will the result be if we want to count the p's in the top row? Well, we'll measure the product SX1, SX2, SX3. So we'll take our state vector and multiply it by SX1, SX2, SX3. SX1 turns the first up to a down and the first down to an up. SX2 does the same to the second particle, and so on for SX3. Notice that this is the same state vector we started with, except for an overall scale factor, or eigenvalue, of -1. That means that, according to the rules of quantum mechanics, we'll always obtain a measurement of -1 for this product. And as we saw a moment ago, that means we'll always count an odd number of p's, as we set out to demonstrate. Now, what if we want to count the p's in the top left shell and the other two bottom shells? To do this, we'll measure the product SX1, SY2, SY3. Again, SX1 interchanges the downs and ups of the first particle, SY2 turns the second up to a down with a factor of I, and turns the second down to an up with a factor of -I. SY3 does the same to the third particle. Multiplying out the common factors, we see that this measurement operator has transformed the state into a copy of itself with the scale factor or eigenvalue of 1. That means we'll always obtain a measurement of 1 for this product, meaning we'll count an even number of p's, as we saw. By the same reasoning, we'll also count an even number of p's for the other two combinations of one top shell and two bottom shells. And this is the result that we set out to demonstrate. So, where does all this leave us? Well, for better or for worse, it may force us to abandon some of the simple ideas that we had about the nature of physical and even metaphysical reality. And there are a number of different theories, ways of thinking about this to try to make sense of what's going on here. And that will be the subject of the next and final video in the series.